All right, what's up, guys? So it's Raj here, here to help you out with the application of Newton's law, specifically the application of a second law, and the problem, example problem I'm going to be doing for you guys. You can find in chapter 4.5, the examples like this and such. And generally, what Newton's second law applies is that, as I have down here. It applies that the acceleration of an object is directly proportional to the net force acting on it. And with that, you can see in this equation right here that if you raise, like say raise or lower the acceleration, it will directly affect the force, that's force of the object. So it'll proportionately lower alongside acceleration, or it'll increase alongside acceleration. And vice versa, acceleration will also increase alongside force if force is increased or decreased. And that's to explain the units also. 1 Newton equals 1 kilogram times meters per second squared. So net force on an object. But then there's also the fact that Newton's second law covers that the acceleration of an object is inversely proportional to its mass. Note the importance between directly and inversely proportional. These two equations in the box right here will help you see that, because force to acceleration, that's a they're directly related. Raise one, you raise the other. Acceleration and mass, on the other hand, they're inversely related. So here, if you raise mass, it lowers acceleration. The heavier an object you have, the slower it'll move. The lighter an object you have, the faster it'll move. Then that's basically Newton's second law. Units here, meters per second squared, force covered in newtons, and mass covered in kilograms. For the most part, that's how it is. Those are the units often used in physics. In our cases, it's okay. And now to help you understand this concept, we're going to take a look at example 4.6 from, up again, chapter 4.5. You'll find that on page 100, going on to 102. And yeah, this is the main example with the traffic light and how it involves like finding three tensions with a stoplight attached to it. And this is also all at equilibrium. As stated here, objects in equilibrium, objects that are either at rest or moving with constant velocity, are in equilibrium, which essentially means force is equal to zero. So yeah, like with the stoplight hanging here, the vertical force will be zero. But let's cover the specific problem first. So okay, a traffic light weighing 1 times 10 to the second newtons hangs from a vertical cable tied to two other cables that are fastened to a support, as in figure 4.14a. This example right here. The upper cables make angles of 37 degrees here to the top left, and 52 degrees with the make 53 degrees with the horizontal bar, you could say, at the top. Consider like a ceiling, or like the traffic light stop that like the bar that extends out to hold the traffic lights. But yes, so 2 degrees right here, those will be affecting how you find the tensions, specifically in whether you use sine or cosine. Actually, with the angles, you're forced to use sine and cosine, so that's mandatory. And find the tension in each wire. So in this example with the picture here, two angles, 53 degrees. Actually, we could take this over. Yeah, like with the, to start off with the helping you to understand this. Like it's first we'll cover tension 3, which is again that equilibrium idea I covered earlier. This stoplight isn't moving whatsoever. It's just hanging off of these cables that are holding it, and it's at complete rest. So that means that its force is equal to zero. That it's not moving or it's not in that constant velocity. If there was acceleration that was added to it or removed from it, to say, velocity would change. But again, it's not moving at all. So easy situation of complete rest equals complete equilibrium. So here, what this means for the stoplight is, if you look at the second diagram here, this means that we can easily find tension 3, which is only the vertical cable. That means working off of the forces of the y-axis, going only up and down, we simply need to use the weight of the stoplight itself. So the force of gravity, aka mass times gravity, and it's already given to us in the problem as 1 times 10 to the second newtons, so about 100 newtons. Yes, and yes. So with 3 unknowns that we need to find, we have to find all 3 of these tensions. We can already easily find tension 3. We can already find that and knock that out of the park. And so now we're going to get to the more trickier aspect of finding the other tensions because they're angled. So you're going to have to do a little bit more algebra-based math to actually figure out T1 and T2. As shown in this little graph here. And okay, then you go on here to, this is what the examples will show. It'll tell you that specifically you need to figure out the forces as they're acting along the vertical axis, aka the y-axis, because this is a 2-dimensional problem. That is very, very important to know. It is a 2-dimensional problem, not a 3-dimensional. So it's only working along 2 axes of the x-axis and the y-axis here. So going along my work here to the example itself. So yes, first, as I already covered, the equilibrium portion, f of y is equal to 0 for the up and down for the stoplight here already. It already tells you the weight. Tension 3 is vertical. The cable itself is vertical, and it's hooked to this. Oh yes, it's hooked to the knot here. The knot is separates T3 from T1 and T2. So T3 only applies to the stoplight. And so f of y is equal to 0. T3 minus the force of gravity here. T3 minus force of gravity here would equal to 0. The forces would cancel out from there to there. And thus T3 is equal to Fg. So T3 is equal to 1 times 10 to the second newtons, 100 newtons. Weight of the light post. Alright. And now moving on to the next stage. This is essentially 3 stages for the specific example problem, which again you can find on page 102 in your textbooks. The second step here is to focus on the specific components, aka what I call the x and the y axes. So, and even more specifically, the forces that are acting along those axes. So, specific components, x and y. This is just to help you label out the equation, the forces that are applying along the x-axis. So here, forces, the sum of the forces along the x-axis. Don't confuse yourself too much with that. It's basically just what forces are going left and right, really, to say. Because yeah, -1. Okay, T1. You notice here is that T1 is going to the left. Like if you were to create a graph here, almost to say, you're going to the left, to the negative end of the x-axis, only focusing on the x-axis here, just the left and right here. So going from that center, 0, off to the left, you're going in the negative direction on the x-axis. So T1 is pulling you to the left, and that's negative. Don't mind it going up. Focus only on it going to the left, because that's what it's doing right now. So for the sum of the forces of the x, that's what we got to focus on. So it's going to be negative T1 times cosine of 37 degrees. Now the cosine of 37 degrees comes from the fact that the angle here is 37 degrees. And how you can take a look at this is that, say in the book, here it switches over the angles, because that's kind of that's the rule of geometry, 2 parallel lines, you could just switch it over, yeah. But yeah, 37 degrees over here, and essentially what it will be is just like a triangle, and 37 degrees, you have to take the cosine of this because you're working along the x-axis, and this is essentially your hypotenuse. So don't mind me drawing on this too much of the term, but I'll erase it, I promise. But yes, so essentially 37 degrees, your angle's here. Now this would normally be going off to the opposite, but you need the x-axis, so you need the adjacent and the hypotenuse. So that'll explain to you why you need to use cosine instead of sine. Cosine is for the x-axis. That's one of the main things. Cosine applies to the x-axis. So okay. So cosine at 37 degrees, yes. And then plus the tension of 2, which is going off to the positive end, to the right. So T2 times cosine of 53 degrees, right? Again, you would have a triangle coming on down here. You would need the x-axis, the adjacent portion, and then the hypotenuse. And the 53 degrees converts over here as such. Dot. So, okay, you're going to add sine of 53 degrees onto it. Minus 1. Oh, and then the minus 1 times 10 to the second, 100. 100 newtons is from the lab. So, oops, sorry, wrong mistake. Wrong mistake there. It's actually, sorry, focusing on the x-axis only. Yeah, it's just the wires, the 2 wires, 1 and 2 here. So yeah, and because they're at rest, it equals 0. So that helps lay out the first x-axis. Lay out the first component, right? And then for a second component of the forces going up and down on the y-axis, you have to apply. Yeah, it's again the 2 cables. They apply because they're diagonal. So they are going in up and down motion. And this time you use the same angles, but this time you apply sine because, yeah, instead, like for T1, instead it's going up, but up in the positive direction because it's the y-axis now. It's going up, and instead you're going to be relying on. Instead you're going to be relying on the opposite. That's the opposite. That's the y-axis that you want. And then the adjacent. Sorry, that's opposite and then the hypotenuse. So sine. Opposite over hypotenuse, you need sine. Right. So okay. T1 sine of 37 degrees plus T2 sine, as you can imagine, of 53 degrees minus the 100 newtons. And this is so because it worked with T3 because your little knot was here, and thus allowed you to apply equilibrium to only this section of the light box. But now you're gonna take it over more to the above space. Take it from all the way from the top, from the cables, all the way down to the light box. So that's why, because its force of gravity is pulling it down, it's pulling it in the negative y direction, you have to make a negative 1.00 times 10 to the second, negative 100 newtons going down. And again, because all of that is sitting in one place, it's not moving at all whatsoever, that all will be equal to 0 for forces. It's all sitting still right there and then. And hey, once you have the two components that you need of the x-axis and the y, of the forces along the x-axis and the y-axis, the third step finally is essentially to do algebra-based substitution. Really, it's taking the 2 equations, you find one variable, and then you put that variable into the other equation. So to show it off, so I'm going to solve for T2. So in the x-axis equation, our first equation, I'm just going to replace, to show you the math, I brought down the entire equation down here, t sine negative T1 times cosine theta, and I added T1 times cosine of 37 degrees, over to the right. I shifted that over to the right, and then I divided out cosine of 53 degrees to the right. I divided that out from the left to the right. So T1 times cosine of theta, and and then it's what we have is T2 equals T1 times I specified the values. I calculated what each of the cosines actually equal to. So this is how it'll look like. Oh, important note, make sure you keep your calculator in degrees, not radians. Otherwise, this could set off your results by about 50 through 70 degrees, and that is obviously the wrong answer. So note that very importantly whenever you do these problems. And so, yeah, you solve this equation, you can simplify it. And so you have T2 equals T1 times 1.33. That's what dividing this gets you. And so you have officially found, now you gotta substitute it. So T2, this T2, like this little substitute you made, you're gonna add that into the other equation. You're gonna add that into the second equation. Just like how you learn substitution in algebra, you're gonna add that into here. Into here. The T2 spot over here. So then you will only have T1 all over. You could just move all the numbers over to the right, and then you could have the variables on the left, and then you could solve for the problem. Solve for that one variable, and then just repeat the substitution again to find T2. The exact value of T2, not this little doohickey here. That's not the exact value. So okay. Shifting over to the left. Sorry if this is a little bit crammed, but here we're using the second equation. Yeah, we're using T1 times the sine of 37 degrees plus this is where we're inputting it. So you see the T2 here, this little portion here, that's T2 now. T1 times 1.33, and then followed by the sine of 53 degrees minus 100 newtons, again sorry if it's crammed, equals 0. And then bring it down lower. We're going to simplify more down. So sine of 37 degrees equals 0.602. Alrighty. So, and here specifically what I did was, sorry, the parentheses may confuse you, but don't let them. It's just t times 1.33 times sine of 53 degrees. So I multiplied sine of 53 degrees and 1.33 and got 1.06. And the times T1 is still there. So minus 100 newtons equals 0, equilibrium. And then simplifying that further down, here what we can do is, because they both share the same variable of T1 and T1, we could just add these two together because there's addition sign here. They share the same exact number, so we can put them together. So yes, we add these two together, we get 1.662. Oh, and also what I did was the 100 newtons that we had from the LiPo, we added that over to the right. We switched it over to the right, and so now, and then just divide the 100 by the 1.662, and you get T1 equals 60.2 newtons. Which is exactly the answer that T1 has in the example here. 61.2. That depends on how your calculator can estimate, like how the exact value that your calculator will give and what significant, what the significant figures you would use. But don't mind that too much. A small difference like that is not a big deal whatsoever in physics. And okay, and then for the exact same thing. So that's the first part of the substitution done. And then the second easy part, you have T1. You have the exact value for T1 now. Now remember the previous remember the equation we used for T2? That more simplified version of T2 we made, T1 times 1.33. Yeah, simply plug the exact value you got for T1 into that equation. So go on here, plug in T1 into that, T1 makes it T2 equals 60.1 times 1.33. You multiply the two together, and then you have T2 equals 19 point... Oops, sorry. bad language, bad writing, but it makes it equal 79.9 newtons. Exactly what it equals in the book. T2. And it even shows the same similar process. So if you need to, again, refer to chapter 4.5, example 4.6, and you get the exact same work that I just showed you right now. 79.9 newtons. So, and also note, again, it's a 3-stage process. You have to identify any components with equilibrium. Then second, you have to do the specific components, X and Y. And then third, substitute. That's just the general basics of how most of these problems work. Some of them will add in additional components or like additional values to find that could expand the problem and make it more challenging to do. But remember that in order on a 2D plane to apply Newton's second law, this is the general 3 steps that you use: equilibrium, specific components, and substitution. And that is how you do. That is how you apply Newton's second law. Hope you enjoyed, and hope this helps out a lot. Peace out, guys. Stay swag.